All right, our lesson today is going to be on derivatives of exponential and logarithmic functions. I'm going to tell you now, this is probably one of my favorite things that we take derivatives of. A couple things I'm going to have to do, and as far as proofs are concerned, will have to actually be later when we learn some other calculus. So for right now, we're going to just look at the derivative of natural log of x. And you're just going to have to take my word for it that the derivative of that is 1 over x. I'm actually going to prove that to you later when we get over into some stuff with integration. It's actually a pretty easy proof. But we are going to look at, for right now, that the derivative of natural log of x is just 1 over x. Now, we're going to take that a step farther because, you know, we're never just going to take the derivative of something that's just an x. So we're going to look at what happens if it's the natural log of some other quantity. So let's say we have the natural log of some u, where that might be a trig function or binomial squared or cubed. And what's going to happen when I take the derivative of that? Well, then what happens is it's a chain rule problem. The derivative of the natural log of something is 1 over something times the derivative of the something. So that's really what you need to memorize, is this 1 over u times u prime. So now we're just going to look at a few examples of how to take those derivatives. Let's look at first the natural log of x squared. Now we're actually going to look at also some reasons why we needed to know properties of natural logs. You'll see that it actually makes some of the derivatives a little easier. So if I take the natural log of x squared using my formula, my idea of the derivative of natural log of something is 1 over something times the derivative of the something. And let's put that 2x over 1. We actually get 2x over x squared, which is just going to be 2 over x. So that's our derivative. And an alternate way that I could do that same problem is to use some of our properties of natural logs. Remember that when we have the natural log of something to a power, one of our properties says the power is going to come down to the front and become the same thing as 2 times the natural log of x. Now, using that, the derivative would be, well, I have a constant times a function. Constant comes down, times the derivative of the natural log of x is 1 over x. I'll think of that as 2 over 1 times 1 over x. And you get 2 over x. Same thing we got using just the idea of the natural log without applying properties. All right, how about this? Y equals the natural log of the sine of x. Then y prime would be the derivative of the natural log of something, 1 over something, so 1 over x, times the derivative of the inside, the derivative of the something, which is cosine of x. Let's throw that over 1. So now we've got cosine x over sine x. But we remember from trig that that is cotangent x, and that would be your answer. Okay. Let's look at y equals the natural log of the square root of 3x minus 5. Okay, here's a place where properties turn out to be really nice. Let's say we think of this as the natural log of 3x minus 5 to the 1/2. Power to the front lets us make this 1/2 natural log of 3x minus 5. And now take the derivative. We've got a constant times a function, so 1/2 comes down. The derivative of the natural log of something, 1 over something times the derivative of the something, so times 3 over 1. So that's going to give me 3 over, and don't distribute through, we'll just leave that as 2 times 3x minus 5. Now again, let's say you didn't realize that you could use those properties of natural logs, and we went just straight from here. Remember, the property goes like this then. The derivative would be 1 over something times the derivative of the something, but think of that as 3x minus 5 to the 1/2. So that would be 1/2 3x minus 5 to the negative 1/2 times 3. just kind of rewriting this, we've got, put that over 1, 3 over square root of 3x minus 5. That's from here. And we've got a 2 from the 1/2, so I'm going to put a 2 down there. Then this is going to the bottom as another square root of 3x minus 5. Let's read y prime. Which is going to be 3 over, put the 2 in the front, and then the square root of 3x minus 5 times the square root of 3x minus 5, just be 3x minus 5. A little more algebra involved with the second method, but it still gets you there. All right, now I want to look at what if it's not a log, but it's a log base something else rather than a natural log. So what if we have like log base 4 of x? Okay. So if I have log base 4 of x, first thing I need to realize is that I'm using change of base formula. I can, in the log of the tall over log of the small, I could make this the natural log of x over the natural log of 4. Now, I know last year in advanced math, or in college math, we changed that a lot to log base 10 of x over log base 10 of 4, but it does change to natural logs. Then remember, natural log of 4 is a number. It happens to be kind of an ugly number, but it's a number. So I could rewrite that as 1 over the natural log of 4, then times just the natural log of x. So just rewriting the problem, now I could take the derivative. Well, this part's a constant. And then times, what's the derivative of the natural log of x? Well, that's 1 over x. So that becomes 1 over, and I'm just going to put the x in the front so it doesn't end up with the natural log of 4, because only the 4s, you're only taking the natural log of 4. So it's 1 over x times the natural log of 4. We can actually extend this to cover any log base a. So let's look at that. So let's say we have log base a of u, where that's not necessarily an x. First thing I can do, and this is kind of a long way, and then we'll show you there's a shortcut. The first thing I could do is rewrite this as the natural log of u over the natural log of a. Now remember, a is a constant. It's a number. U is going to be a function. But then that's 1 over the natural log of a times the natural log of u. So then y prime becomes 1 over the natural log of a times, and then the derivative of natural log of u, we've already talked about that. That's 1 over u times u prime. So really, the derivative is going to be u prime over u natural log of a. So now let's kind of apply that property to this derivative. Y equals log base 7 of x squared minus 1. You're always able to just rewrite this if you want to, or you can use the property. I actually don't like trying to memorize the formula for this. I've got enough things to memorize, so I just go ahead and break this up. Again, if you want to use the formula, and I'll go back in a minute and do that, I would break this up into the natural log of x squared minus 1 over the natural log of 7. But that's 1 over the natural log of 7 times the natural log of x squared minus 1. So what's y prime then? Well, the constant comes down, 1 over the natural log of 7 times, and then the derivative of the natural log of something, 1 over something, times the derivative of the something, over 1. So we'll get 2x over x squared minus 1 times the natural log of 7. Now again, using our formula from a minute ago, that it's u prime over u times the natural log of a, letting this be u, let u be x squared minus 1, and you could go straight to y prime would be u prime, 2x over u, x squared minus 1, times the natural log of a, which was natural log of 7. Again, that's one you're going to have to memorize. if you're going to use that formula, or just remember you can always split it up into two natural logs. Be honest with you, on the AP test, you don't see a whole lot of derivatives when it is not a natural log. There's occasionally one where it's a log base 7 or a log base 2, but not very often. All right, next thing we're going to look at is something called logarithmic differentiation. And the first example I'm going to give you is not really logarithmic differentiation, because it's already set up with a natural log in it. But let's say I wanted to take the derivative of this. So I'm taking the derivative of the natural log of x squared plus 1 cubed over 5x plus 3. So think about for just a minute, if I did the derivative, I would have the derivative of the natural log of something is 1 over all this stuff times the derivative of this stuff. And to do the derivative of that, I'm going to have to do a hody-hop. And then you've got power rule and chain rule and all kinds of ugly stuff going on here. So what we can do instead is apply our properties of logarithms first. So we have a rule that says if you have the natural log of a division or a fraction, you can split that up into the natural log of the top. So take the numerator minus the natural log of the denominator. So that splits it into that. Well, already those are easier to take the derivative of. And we also have a rule that tells us we can take this cubed down and put it in the front and have 3 natural log of x squared plus 1 minus the natural log of 5x plus 3. Now let's take the derivative once we get here. So y prime would be 3 times the derivative of natural log of x squared plus 1 would be 1 over x squared plus 1 times the derivative of the x squared plus 1, 2x, minus then the natural log of 5x plus 3, its derivative would be 1 over 5x plus 3 times 5. So right now we have y prime, we'll put that 2x over 1, would be 6x over x squared plus 1 minus 5 over 5x plus 3. So you can see that what happened here is that by having that natural log in the problem and using those properties, instead of having one big ugly problem, I was able to split it up into two much nicer, smaller problems and take each individual derivative. Now, when you do logarithmic differentiation, what's going to happen is the natural log may not be there for you. So let's say that I ask you to take the derivative of this. Y equals the cosine of x times x cubed minus 1 to the 4th over the square root of 3x minus 2. Again, if we start taking the derivative of that, it doesn't have a natural log in it, but I'm going to have to take the derivative of a fraction, which means I've got to do hody-hop. And when I take the derivative of the top, I'm going to have to do a quotient or a product rule. Plus, I've got the square root in here, so this could get ugly quick. So then what we do is, when we do logarithmic differentiation, we can take the natural log of both sides. So that's the first thing we're going to do. I'm just going to tell you these are going to get to be long, involved problems. They're not difficult, but they do take lots of room. Now, apply your properties of natural logs. Well, that's going to be the natural log of the cosine of x plus the natural log of x cubed minus 1 to the 4th minus the natural log of the square root of 3x minus 2. Now, bringing my powers down to the front, I would have the natural log of y equals the natural log of the cosine of x plus 4 natural log of x cubed minus 1 minus 1/2 natural log of 3x minus 2. All right, now let's take our derivative. The derivative of the natural log of y would be 1 over y dy dx Then the derivative of natural log of cosine would be 1 over cosine times negative sine plus, bring down the 4. The derivative of natural log of x cubed minus 1 would be 1 over x cubed minus 1 times 3x squared minus 1/2. And the derivative of natural log of 3x minus 2 would be 1 over 3x minus 2 times 3. Now I'm going to put everything over 1 so I can get these fractions all kind of simplified and get 1 over y dy dx would equal negative sine over cosine, which I can simplify to negative tangent, plus, I've got a 4 times a 3x squared, so that's going to give me 12x squared over x cubed minus 1. And then here I've got a 3 on the top, so we've got minus 3 over, and again, let's not distribute, let's keep it 2, 3x minus 2. Now the last thing I want to do is, remember, we're trying to solve for dy dx. We want dy dx by itself. So I'm going to multiply both sides by y. So all of this gets multiplied by y. Now here is the kind of tricky, weird part. So I've got negative tangent of x plus 12x squared over x cubed minus 1 minus 3 over 2, 3x minus 2, all times y. But if I go all the way back to the original problem, remember, this is what y is equal to. So now I'm going to put all that down there for my y. I'm going to try to cheat and just copy and paste here. And we're not going to have near enough room. Skip this over some. And put it in that ugly place. Let's pull that down here. And I don't have to really have the y equals. Down. Erase that. And that's the part, that's the y. This is y. So that's the part on logarithmic differentiation. At the very end, you have to remember that, hey, I got to go back and multiply by what y was, which was your original equation. Okay. The AP test is not going to ask you to do any logarithmic differentiation for problems that are that involved. But I do want to use that to now apply to a really, really important derivative, and actually my favorite derivative of calculus. Y equals e to the x. Okay, you're going to think this is cool. So if y equals e to the x, and I'm trying to take its derivative, well, I don't have a clue how to take the derivative of things that are exponential. But I do know how to take the derivative of things that are logarithmic. So what I'm going to do is I'm going to take the natural log of both sides. So I'm going to do the natural log of y equals the natural log of e to the x. But we know that the natural log of e to the x kind of cancel each other out, and we just get x over here. Then I can take the derivative. Well, the derivative of natural log of y is 1 over y dy dx equals the derivative of x is just 1. Now remember what we just said, when you do logarithmic derivatives, you want to solve for dy dx, so we're going to multiply both sides by y. So dy dx is y. But then remember, what was y? Well, y was e to the x. So, prepare to be amazed, dy dx is actually e to the x. So what does that mean? That means that e to the x is its own derivative. If y is e to the x, then y prime is also e to the x. Kind of a cool proof, easy proof to go through. Now we're going to look at what would that look like if we had chain rule, because again, we're not going to just take derivatives of e to the x. So what happens if I have e to the u? Again, where u could be a trig function. It could be a square root of something. It could be some trinomial cubed. Then what would the derivative be? Well, the derivative of e to the something is e to the something times the derivative of the something, u prime. That's just how easy it is. So let's kind of apply that to a few derivatives, and we'll be finished with this video. So let's look at, how about y equals e to the 7x. So y prime, the derivative of e to the something, e to the something, times the derivative of the something. So it's e to the 7x times 7. And then all we would do is just put our constant in the front, because we don't like constants at the end or in the middle of the problem. So we would leave it as 7e to the x. All right, let's try e to the cosine of x. What's y prime? The derivative of e to the something is e to the something times the derivative of the something. The derivative of cosine, negative sine of x. Again, normally we would just put the negative in the front, and then the order of the next two things really doesn't matter. I usually try to put my e's at the end. So I'd have negative sine of x times e to the cosine of x. Let's do some product rule and quotient rule. How about e to the x over x squared? So doing quotient rule, since we've got a fraction here, it'd be ho d ha, the derivative of e to the x would be e to the x, minus ha d ho, the derivative of x squared is 2x, all over ho ho. So that gives me x squared e to the x minus 2x e to the x all over x to the 4th. Well, first thing you should notice is you can actually do some factoring out. Both of these on the top have an e to the x, and they both have a factor of x. So we're going to factor out an x and an e to the x. When I do that, I'm going to get an x minus 2. And that's going to be over x to the 4th. But now that we factored, I could take this x squared and cancel it with one of these x's in the bottom and make that x cubed. So your final answer would be e to the x minus 2 over x cubed. Okay, one more problem like this. And we'll do a product rule. Y equals e to the x, or e to the 4x times the square root of x. Let's let u be e to the 4x. Let v be x to the 1/2, or the square root of x. U prime would be e to the 4x times 4. And v prime would be 1/2 x to the negative 1/2. Do the Jesus fish. We're going to have e to the 4x times 1/2 x to the negative 1/2 plus 4e to the 4x times x to the 1/2. Now I'm going to go ahead and write that without the radical, or without the fractional exponents and negative exponents. So if I do that, this first part here is going to rewrite as e to the 4x in the top, 2 in the bottom, square root of x. My second part is just going to write as 4 e to the 4x square root of x. Now what I'm going to do is I'm going to factor out an e to the 4x. Now, actually, there's some more you can factor out of this, but I think you're going to see this is going to be a little easier. If I take out e to the 4x, I get 1 over 2 square root of x plus 4 square root of x. I could put that over 1, and if you remember the other day when we simplified some problems like this, we're going to go crisscross applesauce, 1 plus, multiply that way, 8, square root of x times square root of x will be x, over, multiply bottoms, 2 square root of x. And that's your final answer. All right, there's one more application to these, and that is, what if it's not e to the x? So let's look at, just quickly, what if I have a to the x, where again, a is going to be a constant. I'm going to do it the same way I did the e to the x problem, and then we'll look for a shortcut. So let's say we had taken the natural log of both sides. Well, that becomes the natural log of y equals x times the natural log of a. Then the derivative is 1 over y times dy dx. Now this next part's a little tricky. This is x times a number. The natural log of a is a number. It just happens to be probably an ugly number, but it's a number. And what happens if you take the derivative of x times a number, like 4x, 3x, 7x, negative 8x? You just get the number. So the derivative of x natural log of a is just going to be the natural log of a. But then we want to get dy dx by itself, so we're going to multiply both sides by y. So dy dx would equal y times the natural log of a. But remember, we can go back, and y was a to the x. So really, it's a to the x natural log of a. So a couple examples of that, and we'll wrap up. I know this has been kind of a long video. Let's say we had y equals 4 to the x. Then y prime would be, and I do actually memorize this formula. You don't have to. You can always go back in a long way. But remember that the formula is that we can do a to the x times the natural log of a. So the derivative of 4 to the x is 4 to the x times the natural log of 4. Okay, let's do another one that's a real simple one. What's the derivative of 92 to the x? It's 92 to the x times the natural log of 92. And what's going to happen is, occasionally, it's not going to be just x at the top. So then let's try something like 3 to the x squared minus 1. Then the derivative of 3 to the something is 3 to the something times the natural log of 3 times, and then the derivative of the something. So the derivative of x squared minus 1 will be 2x. And again, all you could do at this point would be just change the order of things. You might put the 2x in the front or the natural log of 3 in the front. But that would be your final answer. Right, last problem. Let's say we had y equals 7 to the, let's say, tangent of x. So y prime would be, the derivative of 7 to the something is 7 to the something, 7 to the tangent of x, times the natural log of 7, times the derivative of tangent, which would be secant squared x. All right, as I mentioned to you previously, derivatives of natural logs and e to the x problems are the easiest derivatives that you do. Just remember that the derivative of the natural log of something, 1 over something times the derivative of something. The derivative of the e to the something is e to the something times the derivative of the something. And then everything else is just kind of an application to those two rules.